We'll take a look now at the cardiovascular system, the heart and the blood vessels that work within it, the gross anatomy of the heart to understand all the different components, the conduction system, the electrical impulse conduction through the heart to maintain constant rhythmic beating, cardiac action potentials and how they differ from skeletal muscle action potentials, electrocardiograms, the cardiac cycle, the flow from atria to ventricle and out, back through atrium and ventricle. Cardiac output, how much blood mass can be pushed out of a ventricle and how much stays behind. Blood flow, how the blood actually flows from the heart to the lungs and back and out to the system and out to the body. Blood pressure and its components, filtration across capillaries. Will then wrap up our discussion on the cardiovascular system. The heart has inspired a variety of different types of artwork over the years, and it's no wonder because it's such an incredible organ that it would cause so many different points of the arts to represent it in a number of different ways. When we think about atherosclerosis or narrowing of the blood vessels, we can see here a composite photograph showing a narrowed coronary artery at the left. So this would be the open lumen, the space where blood can be transported. And this is how occluded that would be. And a coronary artery would be one of the arteries that's actually feeding the heart. Here then on the right is an even more occluded vessel. You can see these very small amounts of lumen left over to go ahead and help transport blood. But this vessel is in dire need of bypass, or I'm not even sure if a stent could be used here. The location of the heart within the mediastinum, in the area that it sets within the thoracic cavity. We see the mid-sternal line passing right through the middle of the sternum. If we reference the second rib, we can see that being the portion of the heart that's close to the base of the heart. So the base of the heart, counterintuitively noted as the top of the heart, the superior portion, the apex of the heart being this lower curvature. So the sternum helping protect the heart and seeing this deflection of the heart naturally off to the left with the respiratory diaphragm running underneath. Here again, taking a look at the heart's relationship to the lungs, these lungs being pulled back away, the pulmonary trunk feeding out of it, the aorta, the parietal pleura, the lining of the pleural serous membrane that covers the lungs, and the respiratory diaphragm. And notice how the pericardium is attached to the respiratory diaphragm. The pericardium then, as we looked at in our 201 class, is a dual layered serous membrane. So serous membrane meaning that this cavity in between the parietal layer and the visceral layer is filled with serous fluid. So the parietal layer being this external layer, the visceral layer being the layer up against the organ. And the example we used to discuss this was as if you pushed your fist into a balloon. Part of the balloon would go around and touch your fist the whole way. That would be the visceral layer. The other part would loop back around with a cavity for the air in the balloon, and that outer layer would be the parietal layer. And then instead of air being in this middle chamber, we would see serous fluid being in place in that area to help reduce the amount of friction that the heart produces in around 100,000 heartbeats per day. A problem that can occur within trauma to the chest, like say in a car wreck or some kind of blunt force trauma, is that the pericardium covering the heart can actually end up compressing the heart until it stops if there is a bleed or some kind of a sucking chest wound that could bring air or fluid into the space in between the visceral pericardium and the heart. And that condition, being called cardiac tamponade, would mean that the area around the heart and in between the heart and the visceral pericardium would fill with fluid and then end up strangling the heart until it stopped it. Here on dissection, we can see the lungs being reflected away and how continuous the pericardium is with its connection to the respiratory diaphragm. We see how the heart has its deflection off to the left in large part because of the way the liver fits in underneath. And all of this, the pericardium and its continuity, also covering the aorta and the pulmonary trunk as they exit the base of the heart here superiorly. Now, with the pericardium reflected, we can see a naturally fatty heart and this visceral layer of pericardium exposed and the space in between the pericardium and the heart. We'll begin taking a look at the heart from the superior vena cava, bringing blood flow from the upper portions of the body, and the inferior vena cava, bringing blood flow from the lower portions of the body. And we'll be interested in seeing those enter this right atrium. It's covered here with an auricle, and auricle is Latin for ear. So these are like almost elephant ears sitting over the tops of the atria. When our blood flow has come in deoxygenated from the body, we're going to see that go into this right ventricle and then get pushed out through the pulmonary semilunar valve into the pulmonary branch, then out through the pulmonary arteries to then go to the lungs for oxygenation. Returning from the lungs oxygenated will be in these pulmonary veins, now carrying oxygenated blood, arriving into the left atrium, here covered by one of the auricles, a left auricle, transferring now then through the mitral valve into the left ventricle, and then being pushed up and out through the aorta. And off of the aorta, the first organ that is served by blood flow is the heart itself through these coronary arteries. So the very first organ to get fresh oxygenated blood is the heart itself. The coronary arteries, whether we're in a left, a right, the branches for interventricular as we come off of the right and have our right marginal artery. As we take off from the left coronary artery, go around the circumflex artery. All of these different coronary arteries and veins will be of interest to us in the function. And the flow of deoxygenated blood to oxygenation, then back out to the systemic circuit, will be of interest to us. Here we see the posterior view of the heart. We enter in through the inferior vena cava, the superior vena cava, so we have all this deoxygenated blood flow coming into the right atrium, dropping down through the tricuspid valve into the right ventricle, being pumped up and out into the lungs through these pulmonary arteries, coming back oxygenated into the pulmonary veins, into the left atrium, dropping through the left atrium, through the mitral bicuspid valve, into the left ventricle, and then pushing up and out through the aorta to the systemic circulation. You can see a large venous sinus back here. This is called a coronary sinus. You see the right coronary artery over here. And so all of these different coronary veins and arteries happening on the posterior surface of the heart. Deposits of fat on the heart for the ability to convert into energy as needed by the heart. Super amazing organ. Incredible. This internal anterior gross anatomy, we see the right atrium, the right ventricle. The valve that we go through here is the tricuspid. And if you think about tricuspid being on the right side, tri before you bi, then this is the bicuspid valve or the mitral valve. In our left ventricle, we can see this much greater muscle mass on the left side than the right side, pushing out to the entire body rather than just to the lungs. So the heart muscle has a contraction that pulls the ventricles in this way, and then the septum will pull up this way to go ahead and push blood flow up out of these areas. The chordae tendineae here tying on to the papillary muscle, and as the atria fill with blood, there's a natural flow of that blood from the atria into the ventricles. And then we're going to see how once we fill up pressure in these ventricles, then that pressure will close off these valves and then give us our burst of push out through the semilunar valves, pulmonary and aortic, to push blood beyond. The other amazing thing here that we're going to take a look at from a conduction perspective is where we'll see our sinoatrial node and our atrioventricular node for conduction of electricity, and how these nodes are separated from the atria and the ventricles by this connective tissue layer that is not electrically conductive. Here's just a gross anatomy photo of the heart on dissection, external appearance of a normal heart, showing how smooth and glistening the heart is and the epicardial fat that's usual on hearts. The left anterior descending coronary artery extends down from the aortic root to the apex. Just seeing this left anterior descending down to the apex. More of the gross anatomy of the heart, we look at a sheep heart and lungs pluck. And what a pluck is usually a dissection that pulls out a section of organs that are all together. So here we're seeing the lungs with trachea still attached leading into the heart. So an interesting way to do a dissection by seeing all of the organs that are related, say, to respiratory and cardio function in relation to the heart and lungs. This dissection of the sheep heart, similar to what we did in lab, noticing here that we would be taking a look at from a posterior view of the heart being dissected, so that now the left ventricle is on our left, the right ventricle is on the right. So we know that we must be looking at this from a posterior view and leading out to the anterior portion of the heart that would be on the other side of this image. Taking a look at how that tri before you buy the tricuspid and then the mitral valve, these atrioventricular valves leading into the ventricles, and then these ventricles pushing up and out through their semilunar valves to exit the heart either in the aorta or in the pulmonary branch to go to the lungs for oxygenation. The systemic and pulmonary circuits, we hear pulmonary, we think of the lungs, and when we think of systemic, we think of the rest of the body. Usually starting this equation with deoxygenated blood coming from the body superiorly and inferiorly into the right atrium, circulating into the right ventricle through the bicuspid or mitral valve, up through the pulmonary valve or pulmonary semilunar valve, out to the lungs through these pulmonary arteries, being oxygenated in the capillary beds of the alveoli of the lungs and sending oxygenated blood back to the left atrium through the tricuspid valve into the left ventricle, up and out through the aortic semilunar valve to be circulated all through systemic circulation, where in the capillary beds of all of the cells of the body, oxygen is dropped off, carbon dioxide is picked up, and we begin the circuit again. Being comfortable with this circuit is key to understanding a number of components of the physiology of the heart and lungs. The arteries versus the veins, what are the major differences? We usually see differences in coloration, but the big differences are that arteries carry blood away from the heart and veins carry blood back to the heart. And so this is regardless of oxygenation. It's the direction of blood flow in relation to the heart that fully defines an artery versus a vein. aside from smooth muscle differences in their construction, the main thing that we're looking for is that vessel carrying blood away from the heart or to the heart. The pulmonary circuit, once pressure builds up and closes this valve, and then the heart goes through a pulse, it will push the blood up and out to the lungs. Systole or systole is the squeezing of the heart. I use the S in systole or systole to be squeeze. And diastole or diastole is the relaxation as blood is flowing and filling the heart. So relaxation is diastole and pumping is systole. Once we've come from the lungs and we have oxygenated blood, we're bringing it back through these pulmonary veins, and there are 4 of them that will join into the left atrium. When these atrioventricular valves close, that's the lub that we hear in our heartbeats when we're able to listen to them with a stethoscope. So those close with a lub, and then we push blood out through this aortic semilunar valve. And when these valves close by backflow of leftover blood, that's the dub. When these valves close, that's when we hear the lub dub. And keeping in mind that both the left and the right ventricles are emptying at the same time with the systole of the heart tissue, and they're both filling in similar time in the diastole when the atrioventricular valves have not become pressurized and closed. We also see systole and diastole in the atria, but the main systole and diastole that we discuss are in the ventricles of the heart. The heart is fully 2 pumps that are working in series. So we have sort of that upward contraction of muscle, a diagonal squeeze of the muscle, and a twist, sort of like wringing out a dishcloth that pushes the blood in the ventricles up and out. That would be our systole phase. And then we go into a diastole phase where these valves are relaxed for the atrioventricular group, and we're refilling the ventricles, to where then we will have a bit of systole within the atria that will give an additional push of blood into the ventricles, and then the diastole that follows in the atria will allow for the completed filling of the ventricles to then pressurize the atrioventricular valves. Here then, watching just the atria, systole, diastole, systole, diastole, watching the ventricles, systole, diastole, systole. Kind of watching this will help you tie some of that together in between relaxation phase being diastole, the squeeze phase being systole. An additional assist to this whole process is considered to occur through the extra smooth muscle in the arteries that are exiting the heart, especially the aorta. Its additional layers of smooth muscle help it receive the initial push of systolic blood out of the left ventricle, and as it expands the artery, it has a contraction of its own that will actually continue to help push blood out of it. So considered to be a recoil during ventricular relaxation that occurs to keep pushing more blood beyond it. So we have less backflow, and we also have more push into the body. A superior view of the heart valves, this would be our anterior surface here. If you were able to swing yourself around this way and face forward, this would be your heart in your chest. So then when we take a look at this, we can see the shapes of these pulmonary and aortic semilunar valves. Here we can see the tricuspid valve on the right, and the bicuspid or mitral valve, which would be on the left. Kind of a strange orientation here for your view, but if you orient this correctly in your mind, you can make sense of the orientation of these items. We call the bicuspid or mitral and the tricuspid valves also atrioventricular because they're acting between the atria and the ventricles. tied on with chordae tendineae to these papillary muscles inside the ventricles of the heart. On dissection, a tricuspid valve, you can see these three major connection points here, the base of these major muscle connections that are sending up these chordae tendineae or tendinous cords attached to papillary muscle, tied on to this very thin flap. And as the note says here, the leaflets are thin and delicate, just like the mitral valve. The leaflets have thin chordae tendineae that attach the leaflet margins to the papillary muscles of the ventricular wall below. We can see all of the trabecular muscle in here. The semilunar valves then allow for blood to be pushed out beyond them, and then they close so blood that doesn't fully get pushed out of either the aorta or the pulmonary trunk will not come back down into the ventricle and cause problems with overfilling of the ventricle or not sealing correctly. Pretty ingenious design that blood is only allowed to go one way, not the other way. Here, if we take a look at the aortic valve, you can see these three thin, delicate cusps. So this has been cut open and reflected back. And then these coronary artery orifices are the exit points. So the very first place that blood goes is right into a coronary artery to feed the heart itself. And in here, the endocardium, the muscle of the heart that's in the inside, is smooth, beneath which can be seen a red-brown myocardium. So an interesting view where this has effectively been cut this way and then folded back open so that we can see this amazing view of the aortic semilunar valve. Cardiac muscle cells then are very interesting because they have intercalated discs within them, and what the intercalated discs are actually desmosomes and gap junctions, so very connective cellular proteins on the surface, and gap junctions that will keep the handoff of electrical impulse traveling from cell to cell, so that we don't actually have to have nerve innervation throughout the cardiac muscle. We're actually sending electrical impulse through these gap junctions, and that's how a coordinated pulse of electricity can move through the heart and enact all of the heart cells in proper synchronization. Absolutely incredible how these gap junctions work to connect cardiac muscle to cardiac muscle. Here, a zoomed out view, very low resolution, and then as we zoom in, we see these intercalated discs or gap junctions that are existing in between connections from cell to cell. You can also see the nuclei within this. And so this is all the muscle fiber, cardiac muscle, and the intercalated discs with nuclei in the mix. The intrinsic conduction system of the heart is a fascinating system in that if the heart were dissected out of the chest and installed into another person via transplant, the connection from cranial nerve number 10, the vagus nerve, would be severed, and that sever, offering parasympathetic input into the heart, keeps our heart rate around 70 beats per minute. But without that connection, we would see that the sinoatrial node, this node or cluster of cardiac cells held within a sinus area, a little depression within the right atrium, that this specialized cluster of cardiac cells would keep the heart's beat at around 90 beats per minute. The sinoatrial node helps manage the systole and diastole of the atria, as well as sending its action potential to the atrioventricular node that will communicate that beyond this non-transmittal layer of connective tissue that are the valves into the ventricles via the atrioventricular bundle, branching off through the bundle branches and then deeper into the heart tissue, the cardiac tissue in the Purkinje fibers. The intrinsic conduction then is comprised of contractile cells and autorhythmic cells. The contractile cells would be the cells that we would think of as cardiac muscle that will actually go through a contraction. The autorhythmic cells would be those cells that are like the sinoatrial node and the atrioventricular node. Action potentials in the heart are a little bit different than in skeletal muscle. We'll see these atria and ventricular muscles go through a different type of cycle than what we see within skeletal muscle. Here, in contrast to skeletal muscle, we see an abrupt, very rapid rise after threshold to the peak of depolarization. So, similar to skeletal muscle, sodium is entering through the cardiac muscle, but these are fast voltage-gated sodium channels. And a positive feedback cycle will rapidly open many of these channels, and this reverses membrane potential. Sodium channel inactivation ends this phase. So when we're in the end of sodium channel activation, we see our peak. There's a little bit more of a plateau here than what we see in skeletal muscle, because in this phase of our action potential, we have calcium influx into the cell through slow voltage-gated channels. And the cell remains depolarized because very few potassium channels are open at this point in time. And this prevents rapid repolarization, heading back to resting membrane potential. Repolarization then, as calcium channels inactivate and potassium channels open, potassium leaves the cell and we start heading back to a negative resting membrane potential. And also look at the difference in this resting membrane potential that rather than negative 70 millivolts, we're around negative 90. So here, action potential and tension development, just thinking about the tension that's created through this action potential, the tension noted as this purple line that would show the tension that's created, say, within the ventricles, for instance. And so the intrinsic conduction system of the heart being sinoatrial node, atrial ventricular node, these bundles, the branches, the Purkinje fibers, and we're thinking about action potential in relation to the continued firing all the way through to have a complete heart contraction. A typical action potential in the sinoatrial node cell looks like this chart in general. We'll take a look at the different levels of millivolt change that we have, how gradual this change is, and what occurs within a few new terms that we'll see, like pacemaker potential. So in a typical AP in sinoatrial node cells, that we'd see as step one, we have this pacemaker potential. Depolarization is due to voltage-gated potassium channels closing, and a slow inward flux of sodium that begins when membrane potential hyperpolarizes beyond this negative 50 millivolt range, so we drop down in this loop. And voltage-gated calcium channels will open when membrane depolarizes to about negative 55, and this allows a calcium influx. You might wonder, how does the sinoatrial node fire itself? And fundamentally, it's due to these slow channels that are constantly allowing for it to rebuild up to threshold, take off, fire and action potential, reset, slowly build, fire and action potential, and reset. At number two, then, depolarization is due to calcium influx through voltage-gated calcium channels. So in this area where we had usually seen the sodium occur and be a major player, we still do see sodium in the mix, but calcium becomes a much larger player in terms of depolarization of these sinoatrial node cells. In our third step, then, repolarization is going to be due to voltage-gated calcium channels closing. Once they've reached a certain millivolt level, they start closing, and potassium channels will open so that we have that similar potassium efflux or exit out of the cell, like we see similarly in skeletal muscle cells. And we think about if the sinoatrial node were just to fire on its own without any other interaction, then it would be firing at a resting rate of about 90 beats per minute. But we have this parasympathetic vagus feed that feeds into it as well as the atrioventricular node and helps inhibit some of that higher pulse rate. We also have innervation into those nodes, so they're dually innervated with sympathetic feed, which will excite them beyond their normal resting rate. So that similar model we've seen in other organs that has to do with dual innervation, so that we have parasympathetic influence and sympathetic influence at the same time to affect heart rate as needed. Next up, we'll take a look at the electrocardiogram and what it tells us about atrial and ventricular function at any point in time. And so an electrocardiogram, it used to be EKG, still the K meaning cardio, that the ECG is our diagnostic tool when we hook people up with the receivers that will go ahead and receive their heart signals to tell us how their heart looks at any point in time. Here in the P wave, this first hump, what we see, the P wave is showing us atrial depolarization, which is initiated by the SA node. And when the SA node goes ahead and sends that wave of action potential for depolarization, we see a P wave fire. Then with atrial depolarization complete, the impulse is delayed at the atrioventricular node. So we have a little bit of a slight delay in the atrioventricular node, where then our QRS complex from QR to S, we see ventricular depolarization begin at the apex, causing this QRS complex, and atrial repolarization will occur after the S portion of the wave. Then ventricular depolarization is complete in between S and T, and when we get to T, we see ventricular repolarization beginning at the apex, causing the T wave. And then ventricular repolarization is complete after the T wave. So what we're looking at is the complete cycle of a heartbeat in this flow that would be from the atria to the ventricles to ventricular reset. We don't see in here atrial repolarization because it's masked by ventricular depolarization on the chart. In the previous video, we were taking a look at cardiac cycle, and the definition of cardiac cycle is the blood flow during one complete heartbeat. So the contraction and relaxation of both atria, followed by the contraction and relaxation of both ventricles. Systole then is the contraction phase, and again I think of systole to squeeze, so the chamber is empty. And diastole is relaxation phase, where the chamber fills. The general principles of the cardiac cycle then around pressure would say that blood flows from high pressure to low pressure, and contraction by definition is a change in pressure that then creates blood flow in this enclosed system. An increase in pressure during diastole or filling, as a chamber fills, its pressure increases. And then as a chamber empties during systole, then we see a decrease in pressure. The events in the right and left sides of the heart are the same. However, pressures are lower on the right side than they are on the left, due to right side only having to pump to the lungs, left side pumping to the entire body. And some of the size difference between the right and left ventricles, you can see this incredible muscular size difference in the left ventricle as compared to the right ventricle. And it makes sense because the left ventricle has to push a lot harder to get all the way to the tips of the toes and the top of the head than the right ventricle just having to push next door right into the lungs. So let's take a look at some of the events of the cardiac cycle in a little bit more detail, slowed down a little bit than the previous video. Here in ventricular filling in mid to late diastole, we see that the ventricles are filling during this point in time. Pressure is increasing in the ventricles, but they are relaxed. And then we have atrial contraction, which is pushing the balance of the atrial blood into the ventricles. So the diastole that we're talking about here is in the ventricles, because at this point in time, the atria would be in systole. The ventricular systole, we see isovolumetric contraction. So isovolumetric means same volumes in each ventricle. So contracting at the same time, being in systole at the same time, and then ventricular ejection phase, ejection out through the pulmonary and aortic valves, those semilunar valves. Then we have isovolumetric relaxation. The ventricles are relaxing. This is in early diastole. And then we have ventricular filling. So we see an entire cardiac cycle where then we're ready to go back to the beginning and do it all over again. So these are the items that you'll want to be comfortable with in terms of what happens when, and then where does the blood go when it's ejected, where is it coming from when it enters the atria, and those will be some of the key items to keep in mind as we continue with the discussion. So some notables in the cardiac cycle. There's no wave on the echocardiogram to show atrial repolarization. So in this phase right here, this is because it's occurring during ventricular depolarization. So the QRS complex is masking atrial repolarization. We see atrial depolarization, but not repolarization. The duration of the cycle, an average heart beats about 70 times per minute. And each cardiac cycle or heartbeat requires about 0.8 of a second. So 60 seconds per minute divided by 0.8 of a second equals 75 beats per minute. Murmurs then are unusual heart sounds due to improper closure of valves, and the sound is due to turbulent blood flow or flow of blood, which will lead to vibrations in the tissues that can be heard as murmurs. Heart sounds then are produced by turbulence in blood flow, created by closure of valves, not due to contractions of myocardium or slapping of the valve cusps against one another. So again, looking a little bit more in detail at the events of the cardiac cycle, we're going to see ventricular filling, atrial contraction during this mid to late ventricular diastole. We'll see an isovolumetric contraction phase and a ventricular ejection phase during ventricular systole, and then we'll see isovolumetric relaxation and ventricular filling. Looking more specifically at ventricular filling, we see that the atria and ventricles are relaxed during the filling period. The ventricular pressure is low. The atrioventricular valves are open. The semilunar valves are closed, and blood flows from veins into the atria and ventricles, and in this phase, approximately 80% of ventricular filling will occur. In atrial contraction, we see depolarization at the sinoatrial node, both atria at the atrioventricular node, and this is the P wave of the EKG or the ECG. The atria contract and atrial pressure will increase. Blood flows into the ventricles, and here we'll see an increase in ventricular pressure, and ventricular volume is greatest at the end of diastole. The end diastolic volume, or the EDV, is the volume of blood in the ventricle at the end of diastole. The arterial blood pressure is lowest at this point. Diastolic blood pressure will be approximately 80 millimeters of mercury. In isovolumetric contraction, we see the action potential through the AV node, through the AV bundle, down through both ventricles with ventricular depolarization, and this is the QRS complex of the EKG or ECG. The ventricles contract. We see increased pressure in the ventricles, above pressure in the atria, and we see the atrioventricular valves close with no backflow into the atria This is the first heart sound, or the lub. Increased ventricular pressure, no change in ventricular volume, and then when that pressure overcomes the semilunar valves, they will open for ventricular ejection. And approximately 2/3 of the blood in the ventricles is ejected into the arteries at this point in time, called our stroke volume, which is the volume of blood ejected from each ventricle in a single beat. The ejection fraction then is the stroke volume over the end diastolic volume. Arterial blood pressure at highest point, the systolic blood pressure, is 120 millimeters of mercury. Isovolumetric relaxation then, where we see repolarization across the ventricles. This is the T wave of the EKG. The ventricles relax. The ventricular pressure is less than the arterial blood pressure. Semilunar valves close, and this is the second heart sound, the dub of the lub dub. We see a decrease in ventricular pressure. There's no change in ventricular volume. And we're back to ventricular filling, where we see the AV valves open. When ventricle pressure is less than atrial pressure, the ventricles begin to fill with blood, and we're back to the beginning. Another concept we take a look at to get more specific in the output of the heart is cardiac output, or CO. The definition of cardiac output is the amount of blood ejected from each ventricle per minute. And this is key because we realize that we're working within a timeline. Everything that we discuss in this happens during 1 minute. And CO is a measure of cardiac performance. So how much blood is the heart ejecting? How much is it holding on to? This all comes back and relates to cardiac health. The cardiac output then is the stroke volume times the heart rate. And the stroke volume is the end diastolic volume minus the end systolic volume. So that end diastolic volume when the ventricle has filled minus the end systolic volume when the ventricle has expelled its contents. So then usually stroke volume is approximately 70 milliliters that has been pushed out of the heart. There may be 50 or 60 milliliters left inside the ventricle. Stroke volume then, if we take a look at the left ventricle, stroke volume would equal the amount of blood ejected by a ventricle with each beat. We have to think about how much blood can this ventricle hold when it's in diastole, when it's relaxed, and then how much does it push out during systole, and how much is left behind after systole. End diastolic volume, after the ventricle has filled and we're at the end of diastole, we could look at a ventricle that might have about 130 milliliters in it. That's what we'll use for our examples. After blood is pushed out, or the squeeze of systole, the end systolic volume, we could see that that ventricle following systole could have about 60 milliliters left within it. So it doesn't completely empty. This is normal, and it leaves a certain amount behind. In relation to cardiac output, we'll see three factors that regulate stroke volume. The first being preload, or how much can we stretch cardiac muscle as we're in diastole. The idea of contractility, the strength of contraction that the myocardium has at any given preload or end diastolic volume. And then finally, afterload, or the pressure in the aorta that has to be overcome by the ventricles so that they can eject blood during systole. In this concept then, for cardiac output, the stroke volume preload, we refer to an item called the Frank-Starling law of the heart. And Frank and Starling were physiologists in the late 1800s who did experiments on frog hearts that were then looked at as being indicative of a formulation of this law around 1914, so the early 1900s, that said that within limits, the stretching of cardiac muscle fibers will intensify the force of their contraction. So the more we stretch, kind of like blowing up a balloon, the more we stretch that cardiac muscle, the greater the contraction will have. Within this idea, then, we come back to some of our ideas around cross-bridge formation and length-tension relationship. So the idea that myosin and actin filaments can be stretched to a certain extent, and cardiac muscle, not being attached to bone like skeletal muscle, can stretch quite a distance as needed, like during exercise or other demands that are put on the heart. And all of this comes back to the myosin-actin relationship and how much stretch we can have before we have a muscle contraction. The preload on the sliding filaments, again, sort of a reminder from skeletal muscle that when we're in a resting state, we have a certain overlap of myosin and actin. As we have our contraction, we start to pull those fibers together, and then we have as much overlap as is possible that will create the full contraction. The idea reminding ourselves that we have our myosin heads that are able to connect with actin once the troponin tropomyosin complex is removed. We have our stroke of the myosin head that goes ahead and creates the contraction. And then we have the reset of the myosin head through ATP. And in this idea of preload, then, we have our end diastolic volume, which creates stretching in a ventricle, which is going to increase the force of contraction and then decrease the stroke volume because the volume is being pushed out, which will then increase our cardiac output. The one that may seem counterintuitive is a decrease in stroke volume. But if you think about the volume moving out, if it was originally counted here, this volume definitely decreases when we overcome either an aortic semilunar valve or a pulmonary semilunar valve. And all of this amounts to what will end up being our cardiac output. So some of the factors that determine the end diastolic volume will have the length of ventricular diastole, or the filling, as well as venous pressure. In the length of ventricular diastole, an increased heart rate over 160 beats per minute will decrease the end diastolic volume because the ventricles contract before they're adequately filled. So if we're working out or something, we'll be emptying those ventricles because they won't have time to completely fill. A decreased heart rate then has the opposite effect, where we'll see an increased end of diastolic volume amount of blood left in the ventricle after contraction. In venous pressure, we see an increased pressure of blood returning to the heart, which increases venous return and stretching of the ventricle wall, which increases the filling, which also increases the end diastolic volume. We'll see this increase in exercise. The cardiac output stroke volume relationship with contractility then would say that the strength of contraction of the myocardium at any given preload, or the preload being our end diastolic volume, is increased by positive inotropic agents. And an inotropic agent is an agent that would modify the force or speed of contraction of a muscle. Sympathetic nerves can do this, the autonomic nervous system leading to the heart with beta-1 receptors on the heart. Calcium hormones like thyroid hormones, epinephrine and norepinephrine on those beta-1 receptors. Digitalis, a plant extract, is also an external component that can increase contractility of cardiac muscle. Contractility can be decreased by negative inotropic agents. So if we have increased extracellular potassium, this will depolarize the membrane and can lead to inactivation of the voltage-gated sodium channels. Acidosis, or a high level of hydrogen in the bloodstream, this getting into the cardiac cells can decrease calcium into the cardiac cells. And we see decreased calcium then, as well as calcium channel blockers. All of these can reduce contractility. Some of this may be desirable, reducing contractility of the heart, if we've lost some of our sinoatrial or atrioventricular node function. And a myocardial infarct that damages cells, infarction being cell death, could also decrease contractility of the heart just through a frank loss of the quantity of cells in the heart. The cardiac output stroke volume afterload discussion would say that the pressure in the aorta that must be exceeded by the ventricles to eject blood during systole is this afterload, and this is an impediment to an ejection and represents the load against which the ventricles exert their contractile force. Fundamentally, afterload is the resistance of these semilunar valves to the pressure that is trying to push out through the ventricles. So we have to overcome afterload to have our complete ejection of blood. As we continue to take a look at afterload, we need to realize that as we have increased afterload, we're going to have decreased stroke volume because it's difficult to get more blood beyond a greater afterload pressure. So before we get to afterload, we take a look at preload, of course, and preload is the volume of blood in the ventricles at the end of diastole, or the end diastolic pressure. This preload pressure can increase in hypervolemia, or more fluid in the blood. If we have sodium, potassium imbalances, issues with the kidneys, other problems, we can see hypervolemia or high volume. Regurgitation of the cardiac valves can allow for regurgitation into the ventricles, and then we can also see problems in preload with heart failure. Afterload then would be resistance that the left ventricle must overcome to circulate blood, and we would see this increased in hypertension or in a closing of the vessels on the other side of the ventricle, as well as vasoconstriction that would be caused with that. And the idea that increased afterload increases cardiac workload, and we see a diminished stroke volume because of that. In relation to cardiac output, our heart rate, the resting adult average heart rate is 75 beats per minute, and the vagal tone keeps it at this rate. The vagal tone being from the vagus nerve, cranial nerve number 10, that is a parasympathetic nerve, and helps keep the heart rate at that rate, because otherwise the average heart rate would be around 100 beats per minute if it were set strictly by the atrioventricular node and the sinoatrial node. And we looked at this a little bit earlier, but the autonomic innervation of the heart is dually innervated by our central nervous system through the peripheral nervous system. In our parasympathetic division of the autonomic nervous system, we see the vagal fibers from vagus traveling the sinoatrial node and the atrioventricular node. We also see then the sympathetic fibers traveling through the sympathetic chain to innervate the sinoatrial node, atrioventricular node, and other direct innervation points to speed contraction of the heart. Parasympathetic innervation then is going to hyperpolarize the membrane of these autorhythmic cells, the autorhythmic cells being the sinoatrial node, the atrioventricular node. And the goal here will be to slow depolarization, so in that slow heart rate, here we see that we have a cardioinhibitory center in medulla oblongata that has parasympathetic neurons that are going to release acetylcholine, which will inspire an increase in potassium efflux or exit out of the cell membrane, and a decrease in calcium influx. Both of these items hyperpolarize our cardiac cells, and this hyperpolarization decreases the rate of depolarization, which decreases heart rate. The flip side of that is sympathetic innervation, which will depolarize membranes of autorhythmic cells and speed up depolarization. So if we see a normal path here, this sympathetic innervation is going to speed that up. Cardioacceleratory center in the medulla oblongata, which interacts with sympathetic neurons, releasing, say, norepinephrine. This release into the cardiac muscle will inspire an increase of sodium and potassium influx into the cell. We know that when we bring in more positively charged ions into the cell, we're going to depolarize more rapidly, and this is going to increase heart rate. Sympathetic innervation then, the epinephrine and norepinephrine from the adrenals will open these voltage-gated channels for a longer period of time, and will also increase calcium ATPase on the sarcoplasmic reticulum. So remembering the sarcoplasmic reticulum is the storage for calcium. This epinephrine and norepinephrine will activate this regulatory protein to allow more calcium to flow out of the sarcoplasmic reticulum, which will activate more cardiac cells. We'll see an increase of calcium stores in the sarcoplasmic reticulum, as well as an increase of calcium being released for an increase in contractility of cardiac muscle. Continuing on this idea that we simultaneously have calcium being removed from the cytosol faster, shortening the calcium troponin binding time, which then allows for a shorter duration of contraction And since we're still putting calcium into the cytosol, we can see that we will stop contractions and start them much more quickly with this combination of releasing calcium and removing it. And what the end result is an increased heart rate. So again, looking at this, the heart rate and contractility sympathetic innervation, we're releasing more calcium from the sarcoplasmic reticulum, and then we're uptaking more calcium, removing it from the tropone and tropomyosin complex to then help allow for the reset of myosin heads more quickly. So these heads will go ahead and connect more quickly and reset more quickly with this type of sympathetic innervation. When we think about cardiac output and heart rate, we also have to think about how hormones affect this equation. Here we look at epinephrine and norepinephrine, also thinking about mimic sympathetics. So mimic sympathetics would be components that can mimic the activity of epinephrine and norepinephrine. We might be thinking about something like nicotine, for instance. Caffeine can sometimes have some similar outputs or effects on the body as epinephrine and norepinephrine. Thyroid hormones can increase heart rate through an increase in metabolic rate. And if we see a very high heart rate over 100 beats per minute, we call that tachycardia. And a heart rate that's less than 60 beats per minute would be called bradycardia. Some other factors that can affect heart rate: with age, heart rate decreases. And in gender specifics, the heart rate is usually faster in females. A little bit different relationship between thyroid hormone in many cases and the heart. Emotions can affect the heart rate. If we have increased emotions or charged emotions, we can elicit the sympathetic nervous system. Exercise as well increases the sympathetic nervous system, which increases heart rate in turn. Some other factors that can have an impact on heart rate: if we have a fever from some kind of a disease process that increases our temperature, we can also see an increase in the metabolic rate in heart cells, which will increase heart rate. Our physical fitness: if we see an increase in physical fitness, we'll see a decrease in heart rate. The reason for that is that increases in cardiovascular fitness cause physical changes in the structure of the heart. And we see a thickening of the muscles of the heart wall. The heart pumps more blood with each beat, and this increased efficiency means that an athlete's resting heart rate will fall to a level that could indicate trouble in a non-athlete. Many athletes don't realize that high levels of conditioning also cause heart symptoms that doctors might mistake for serious problems like bradycardia. The strength of the heart is so much greater, it can move more blood with fewer beats, and this in turn will decrease heart rate. Heart hypertrophies increase our stroke volume, hypertrophy being increase in heart mass, and then our cardiac output is maintained even though we're doing fewer beats per minute. So here, if we take a look at an increase in exercise by skeletal muscle and respiratory pumps increasing, exercise will lower heart rate, allowing more time for ventricular filling, which will increase venous return and increase the end diastolic volume, the preload, which will then increase stroke volume and increase cardiac output. We also see that upon exercising, blood-borne epinephrine and thyroid hormone, as well as excess calcium, can be released to increase contractility of the heart and decrease the end systolic volume. So the amount that's pushed out is greater. There's less of it left behind, so there's less end systolic volume. That, coupled with a greater end diastolic volume, amounts to greater stroke volume. We also can see similar outputs from exercise, fright, and anxiety, which would be an increase in sympathetic activity and a decrease in parasympathetic activity that can also increase heart rate and then increase cardiac output. When we look at blood flow then, we're interested in seeing that blood flow is driven by the heart pump through closed channels or blood vessels, and blood flows from high pressure to low pressure. So we see a movement from arteries to capillaries and back through veins. That's what this chart is showing, that if we start at the aorta, we see a really wide diameter vessel that has a very high blood pressure. It also has a rebound within its structure. So as we move from the aorta to supporting arteries to arterioles, we see that these vessels have more smooth muscle, and so they have a rebound in their pulse or in their response to blood flow that also assists with blood flow. And then by the time we're out at capillaries, our blood pressure has dropped significantly. And then as we get to venules and veins and the vena cava, our pressure is dropped significantly from where it began. So circulatory pressure is the pressure difference between the aorta and the right atrium. So thinking about the aorta being maximum pressure, the right atrium being the least as everything's returning. Compare 100 millimeters of mercury to going to 0 millimeters of mercury in this difference. Blood flow in arteries near the heart is pulsatile. That's these pulsations in here. Due to the elastic recoil during ventricular diastole, we have this recoil of these arteries when the ventricle is being filled. And that's because blood stretches the walls of the arteries and blood vessels recoil on the blood with force. And this pulsatility is dampened by the time the blood reaches the arterioles. You see that drop. And so we've lost a lot of that elastic recoil by the time our vessels have reduced in size from arteries to arterioles. When we look a little bit more at blood flow, we see that larger arteries are distensible or stretchy, but arterioles are not. So by the time we've left the aorta and arteries and we reach arterioles, we see that they're not as stretchy as arteries and the aorta. Part of the reason for that is that arterioles damp pulsatility and help reduce that pressure as we get into the finer capillaries and venules. Pulse pressure is going to equal the pressure of systole minus the pressure of diastole. And mean arterial pressure, or MAP, the pressure in arteries averaged over time, is going to be measured by the pressure of diastole plus 1/3 times the pressure of systole minus the pressure of diastole. And you can see from this calculation that it's weighted towards diastole because diastole lasts longer than systole, and MAP is measured over time. Here, when we take a look at a capillary bed, we see this concept of blood flow as it goes from larger vessels to smaller, and the vastness of these capillary beds is equated in your book from going from a river through tributaries out into a lake. And so we have a pretty significant drop in pressure. So the velocity, if we're out here at a large artery, as we enter into the capillary bed, how much that drops. And then it regains some as we increase the size of the vessels that we're exiting with. So this lower chart is a measure of velocity based on the size of the vessel. The upper item is showing the total area of the vascular bed. Here, if we're just in an artery, there isn't as much area as when we've gone out into a capillary bed. And we see an inverse relationship between a greater amount of area equaling a lesser amount of pressure. The inverse nature of the chart, how it's almost a mirror of itself, would say that less area equals higher pressure. More area equals lower pressure. So that's really what this is showing, is how we go from a vessel to a capillary bed back to a vessel. And then the same thing with velocity, from a vessel to a capillary bed back to a vessel. And here then, in the cardiovascular system, flow varies. When we see an increase in cross-sectional area, we'll see a decrease in the velocity of flow. Our final point of discussion for this lecture is blood pressure. We'll take a look at what blood pressure is, that it's considered to be the force exerted by blood as it presses against the walls of blood vessels. And clinically, we refer to pressure in systemic arteries. So when we're measuring blood pressure, we're measuring the blood pressure of arteries rather than veins. Some physical factors: the blood volume and arterial compliance, or the stretchiness of the walls. Physiological factors: points of control on a moment-to-moment basis, so that cardiac output equaling stroke volume times heart rate, where we take a look at also resistance to blood flow, a large R for resistance. Some physiological elements that we need to look at. The physical factor of blood volume would say that blood pressure varies directly with blood volume. And this makes sense because if we have hemorrhaging, we see a decrease in blood volume and blood pressure. If we have high sodium and water retention, we'll see an increase in blood volume and blood pressure. Arterial compliance, then, is another physical factor. If we see stretchy arteries, we see less pressure. If we see stiff arteries that can't stretch, like in an atherosclerotic issue, then we'll see high pressure. We do see an increase in stiffness of the arteries with age. A physiological factor of cardiac output, we would see that it's the main determinant of blood pressure, and blood pressure varies directly with cardiac output. Cardiac output equals stroke volume times heart rate. If we go back to that equation, and we see a direct correlation between cardiac output and the quality of blood pressure. The resistance to flow has to do with friction and also constrictions that may exist within vessels. This would be an impediment to blood flow or a blockage. And two main factors that most influence resistance factor are the radius of the vessels and the viscosity of the blood, as well as total blood vessel length being mixed in as part of that. So if we look at the blood pressure resistance equation related to the radius, we would see that resistance is proportionate to 1 over the radius to the power of 4. And what we're looking at is laminar flow, which just means a central stream of blood flowing the fastest. Streams close to the wall are retarded by frictional resistance. They're held back. And so it stands to reason that if we have a larger radius vessel, say if we go from a 1/2 inch vessel to a 1 inch, we're going to see a proportionate change in the size of that radius equaling a reduction in resistance. So if you increase the radius by a factor of 2, resistance to flow drops to 1/16 of the original value. Just again saying that if you take a 1/2 inch vessel and you raise it up to an inch vessel, then this vessel will have a lot less resistance than the 1/2 inch vessel. And so then remembering that flow is proportionate with 1 over resistance. In relation to blood pressure, resistance, and viscosity, we see that there's internal friction that affects the flow of blood. So just natural frictional resistance inside vessels. And then we look at hematocrit, which would show us a percentage of blood that is packed with red blood cells. So we would expect that if we have an increased hematocrit, we have increased viscosity, which increases resistance, which decreases our cardiac output. So thinking about why too many red blood cells or too few red blood cells could impact hematocrit and then viscosity, resistance, in our cardiac output, there's a direct correlation that if we fall out of homeostasis in relation to the creation of our red blood cells, we could be in trouble. So we must increase pressure to get a given velocity of flow. And the only thing that we can vary in the equation to increase pressure is the heart. and having it expand in size or become hypertrophic to try to overcome any of these blockages or resistances is usually why we'll see hearts that are enlarged in individuals that have heart disease or arterial vascular disease. If we think about total blood vessel length in relation to blood pressure, we realize that this is a factor as well in considering blood pressure. And for instance, 1 pound of fat has over 200 miles of capillaries within it. So we have a lot of vasculature in our body, and this has an impact on, we have a lot of vasculature in our body, and this has an impact on our blood pressure as well. So factors that influence blood pressure, we see blood volume is important, cardiac output is key, peripheral resistance, that resistance within the vessels, and then compliance, or the ability for the vessels to be somewhat flexible. These are all going to be factors that influence blood pressure. If we take a look at autoregulation, local conditions that regulate blood flow, we want to take a look at a normal vessel, and then what happens if that vessel is vasodilated or opened up, or if it's vasoconstricted and closed down. When we look at this as a myogenic mechanism, we see myo is muscle and genic is the creation. So the creation of this mechanism, the way that these vessels vasoconstrict or dilate, is based on the changes that happen in the smooth muscle that are within these arteries. So if we see an increase in stretch in these arteries, then we see vasoconstriction. If we see a decrease in stretch, then we see vasodilation. So do these vessels tighten up and constrict, or do they relax and dilate? As far as metabolic control is concerned within this autoregulation, we see the release of metabolic chemicals by tissues like carbon dioxide, hydrogen, prostaglandins, histamine, nitric oxide, adenosine. These can all affect the regulation of blood flow. When we look at blood pressure control, we think about short-term mechanisms and long-term mechanisms. In the short term, blood pressure can be controlled by neural and hormonal impacts. In the long term, most of our control over blood pressure will be hormonal. Some short-term controls that we look at within blood pressure would be a fast response to changes in blood pressure or the mean arterial pressure. And this would be responsible for moment-to-moment regulation of our blood pressure, where we see neural controls or baroreceptors, which are stretch receptors that exist in some of our large arteries, chemoreceptor-initiated reflexes, and the influence of higher brain centers that can quickly adjust blood pressure. Then we see some short-term hormonal controls like epinephrine and norepinephrine from the adrenal medulla, angiotensin II, atrial natriuretic peptide, or ANP, and then we also see antidiuretic hormone. If we look at the baroreceptor reflexes, some examples of this could be within the carotid arteries that are within the neck, as well as the aortic reflex within the aorta. The carotid sinus reflex maintains normal blood pressure in the brain using baroreceptors that are located in the carotid sinuses, or the walls of the internal carotid arteries, to communicate stretch. If blood pressure is too high or too low, the stretch will indicate that, and correct measures can be instituted through response to these reflexes. The aortic reflex will maintain normal systemic blood pressure through the feedback that baroreceptors send to the brain, and these baroreceptors are located in the wall of the aortic arch. On dissection, we don't see these items in the gross anatomy, but they are these clusters of cells that have stretch receptors built into them that we specifically call baroreceptors. An example of how these baroreceptors work is in an instance where we have increased blood pressure. We can see the baroreceptors are stretched and increase their action potential frequency, which sends that signal along cranial nerves number 9 and 10 glossopharyngeal, and vagus. And what comes of that then in terms of the sensory component then goes to the cardioinhibitory center, which also can be the cardioacceleratory center, as well as the vasomotor center. So we're looking at vasomotor being the control of constriction or dilation of arteries. Here then, if we follow this path, we see the parasympathetic activity of the vagus nerves is increased and the sympathetic activity is decreased, which in turn reduces heart rate and contractility and reduces cardiac output, which reduces blood pressure. On this side with the vasomotor center, the sympathetic activity is reduced, vasodilation, so the arterioles open, and peripheral resistance is reduced, and we see blood pressure drop. And that was the response to increased blood pressure through the reception in baroreceptors in the aorta and the carotid arteries. If we take a look at a scenario where we have lower blood pressure, then we see inhibition of the baroreceptors and a decreased action potential frequency using the same sensory nerves 9 and 10, glossopharyngeal and vagus. The same centers of the medulla oblongata are engaged. The output, however, though, is an increase in sympathetic activity, a decrease in parasympathetic activity, which increases heart rate and contractility, increases cardiac output, and combined with the vasomotor center, which increases sympathetic activity, which increases vasoconstriction, increasing peripheral resistance, increases blood pressure. So when we constrict these vessels, we increase blood pressure. So all of this in response to lower blood pressure. The short-term control of blood pressure, again, neural influence of higher brain centers, can alter the blood pressure by sending input to those medullary cardiovascular centers in the medulla oblongata, like the cardioacceleratory center, the cardioinhibitory center, and the vasomotor center. In an example of this, during an emergency or fight or flight response, the hypothalamus acts to increase blood pressure via input to the medulla. Epinephrine and norepinephrine from the adrenal medulla function the same as sympathetic innervation, and we see an increase in cardiac output and an increase in vasoconstriction. Angiotensin II is also a potent systemic vasoconstrictor. The short-term control from the hormonal perspective, we see atrial natriuretic peptide, or ANP, being synthesized by the atria of the heart and secreted when the atria are stretched. This will increase sodium and water excretion by the kidneys. Then we can also see ADH, antidiuretic hormone, also noted as vasopressin, released in response to small changes in osmotic pressure, and also released when blood pressure drops dramatically. So we see vasoconstriction occur with vasopressin, or antidiuretic hormone. Long-term control, the renin-angiotensin-aldosterone system, adjusts blood volume, and this is a slow mechanism. This discussion is a bridge into some of our discussion that we'll take a look at when we focus more on the kidney in our urinary unit, as well as our lungs in the respiratory unit. But a cascade of events that responds to dehydration or hemorrhage, where we see an amazing interplay between the kidneys releasing renin, the lungs releasing the ACE lung enzyme, the relationship of all of this with angiotensin 1 and 2, the pituitary gland getting involved, antidiuretic hormone, vasoconstriction, water reabsorption in the kidneys, a really amazing cascade of events that is central to our water management within the body. Another piece of this that we'll be taking a look at in our urinary unit will be bulk flow across capillaries, and we'll take a look at arterioles, a capillary bed, and venules with interstitial fluid, and then how hydrostatic pressures of the capillary and the interstitial fluid, as well as relationships with osmotic pressures of the capillary and interstitial fluid, will work within the capillary bed to affect the bulk flow of fluids and ions within these capillary beds.